see if this is working. Now, I have to give YouTube a couple of seconds to warm up, but while I'm doing that, I should probably introduce what we're doing today. So, I have wanted a custom LED light kit for my Mini Zs for a while. I don't really feel like the LEDs on the standard Mini Z quite cut it, especially if you want things like indicator and, well, I suppose it's got the brake lights, but I want the indicators to go off when I turn and the brake lights to be adjustable and flash fancy patterns. So what we're going to do is build a controller board, plug in some smart LEDs to that controller board and see if we can get them to light up. And once we're at that stage, we're actually somewhat basically complete. As you can see, I've actually got the data sheet for the smart LEDs in front of me. And I'll be pulling in some additional information shortly. So I'm actually using the Neo sticks from Adafruit. I actually found I had them laying around the other day. A bit hard to see on camera. I can probably... Oh, that's getting really bad reflection. But that is fine because I can now disable autofocus, update that, and there we go. Let's bump it even closer. There. So nice and tiny. Not looking too bad. Okay, just sending some people some messages. So this is going to be a very messy stream, and I do apologize for that. I could have done a lot of the work beforehand, but I'm assuming here, and I may be wrong, that some people may want to see my process. And people hopefully inspire some people, which my previous projects seem to have done that. I got a lot of positive feedback from a small part of the community in regards to the winch, but to be honest, I got very few views on that video, so that sounds like that's people don't want that content in particular. Either that, or I also somewhat suspect that Google might have been having a bad day, because there's some unusual traffic numbers on that. So we're going to start off by stripping some wire. Now I've made a mistake there. So already we can see that the stream hasn't started particularly well. This is going to be a very raw stream. So I've got as I said, the LED strip with 8 LEDs on it. I've got a much larger board for later. Originally this was going to be the brake light, a programmable brake light for my e-bike. Hence why I've got all this stuff laying around, but I ended up getting a better e-bike. So I'm going to work on these smaller strips so that I've got I can make them into traffic lights or street post lights, or down lights for the RC car. And I've also got a micropython board. And I don't know if that's going to like focusing, but that doesn't matter. You don't really need to see the details. I'll pull up the data sheet later. As you can see, this is literally the size of my thumb. So yeah, it's pretty tiny. And I found that there's boards that are even cheaper than this and smaller. So the final product, which I may actually even end up selling online, will be significantly smaller than this. The reason I like this board is it has built-in Wi-Fi and Bluetooth. So the idea is that you're going to be able to configure the LEDs and the lights on the car over Wi-Fi, which will be a lot of fun. And you can get accelerometers and stuff, so I'll be able to export that. And who knows, originally I intended to have a full racing platform served up via Wi-Fi on this thing. And lights was just one part of it, but I've decided to start with the lights. So I'm going to start stripping the wires and doing the soldering. And then we're going to get onto the micropython board. We're going to be using some interesting techniques on the micropython board, so definitely stay tuned. And if you have any questions during the process, just chuck them in chat. I might even consider making the chat available after this video goes live as well, rather than turning it off, but I guess that's really going to depend on if anyone comments or not. Okay. There we go. Now we play with my new favorite toy, which is a wire stripper. Now the lighting is not the best today, and I'll be honest, I don't really care to do good lighting since we're mostly going to be focused on this area here. Let's jump back to the documentation, and yeah, so we provide it with 5 volts, we've got data in, data out, so It's a nice 3-pin protocol. It's relatively easy and simple to work with. Each LED takes about 18 milliamps. We've got 8 of them on board here, so that should be 160 milliamps by my calculations. And this can pull a maximum of 100 milliamps from the USB bus, so we should be safe in that regard. We're going to do some other interesting techniques as well, which is cleaning the contact terminals with a scourer. Now, a lot of people use stainless steel wire. I've taken a liking to scouring pads because stainless steel wire is conductive, and I have seen shorts because of it before. But if it's all you've got, just make sure you keep everything clean. 5 volts DC, ground. Oh, I didn't need to strip that. I could have left that. Oh, whatever. Doesn't matter, I'm not going to complain. So we're going to use my TS80P soldering iron, which I absolutely love. If you give me half a chance, I will rave on and on and on about it. So we're just starting up now. Let's see if I can get that closer. And one push. So I'm only running it off Qualcomm Quick Charge 3.0, so it's only drawing 18 watts. This will go up to 30 watts, but as you can see, it heats up pretty quickly, which is really nice. And once it hits about 300, it's generally pretty good to work with. In fact, I'm actually going to drop the temperature because I've got this set to 400. Oh, it's actually really, really hard to do this without looking at it, so... So as you can see, it's pretty simple to change. And we give it a sec. And you can see it's now stabilized. So fairly simple. We're going to do my usual trick, which is to tin the wires first. And let's jump around because I've got people pinging me in chat. Huh. Yes, funny. So people are trading war stories at the moment, and I kind of miss that. So I actually used to work in the web space in IT, and wow, did I see some things. Okay. Actually, I saw some things today. Like I had a guy say, "Oh, let's do Amazon, do AWS." S3 and everything like that, and I said, oh, that's fine, but your task is pretty simple, like why don't you use a web server? And I basically got the question back, what the hell is a web server? And it's like, well, you know all those S3 and Amazon services, what do you think's running those services? Kind of blew my mind, and it reminded me why you should never let interns make technology decisions that they're not going to be responsible for maintaining after they leave the organization. But I'm not bitter at all. Great, my hand's shaking a bit. This is going to make things difficult. Okay. And now we hold that. Just going to do nice quick soldering jobs here. Not really worry about it too much. Great, I created a solder bridge. That was not good. Don't want that to short. Let's take a closer look. Might be able to save this one. If not, I've got like half a dozen of these modules, so... And I've got so many neopixel LED things now that... Turns out there's a couple of really cheap places you can buy imitation clone ones. And the official ones are really, really, really expensive in comparison. Cool, and that's actually unsoldered the other joint, but it's also fixed my short circuiting problem, so that's good. Just quickly hold the soldering iron in my mouth. That should be safe, right? Okay, and we're nearly done. Unfortunately, this is the easy part. Now, we're lucky in that I'm going to call this a win if we get some LEDs to light up, and a double win or a bonus round if we can get it to play an LED pattern. Luckily, if we can do the former, the latter is like a 30-second job. So let's leave that there, which is dangerous. Don't do this at home. Now I've got to solder pins to here. I need 5-volt ground and SPI out. Actually, we'll disconnect that. And I'm just going to use a cable holder to rest this on. There we go. That should keep everything safe. Awesome. So let's bring up the diagram. So I'm looking for a very, very specific MicroPython board, and it can be a bit difficult to get the information on it. It's not microbit. Should just be the PyBoard 2.0, but I need a pinout for that. So docs. Oh, actually, you know what? The trick is actually to go via the store. Yeah, that's the one I want, the D series. So let's have a quick look while I'm at it. 200 megahertz processor, 512K flash, 256 RAM, and 2 megabyte of external RAM. I think this is also the bottom end model. Yeah, this is... So you can get even more flash and RAM. You can get 4 gig MMCs. The 1.0 board actually has a SD card slot on board, which if you're running a web server on it, turns out to be really, really handy, because you can do most of the work in the client's browser via JavaScript and just have a simple API. Yeah, so this has now got 2 megs of flash ROM and half a meg of RAM, which is plenty. Like, as long as you've got about 128, MicroPython generally runs pretty fine. 128 kilobytes, that is. So let's pull this up. Let's look at that. That's what I want. SDA, SD, SCL, so that's a CAN bus and the I2C bus, which I don't want. I do want 5-volt USB. And I want SPI. So that's the enable pin, that's a clock pin, that's the output pin, and that's the input pin. Since we're going to be sending data out, we want the output pin, and that's only that. We're going to be using a technique called bit banging, because this board can't talk the LED protocol natively, which looks like this. You use this to send a 0 and that to send a 1, and then you reset the line. So we're going to fake it by turning the pin on and off rapidly, and we're going to leverage the SPI hardware to send out, how do I say it, 8 time intervals at once. So we can let the SPI bus turn the pin on and off 8 times at a set period, which means what we have to do on the software side is significantly simpler. Really, really nice trick, that one. So we need this, and we need micropython.org, python.org. We need 2 things from the micropython.org webpage. I need some reference about the 5-volt or the V+. V+ 16, supplied by the USB when USB connected. Okay, so we need to use this pin here for positive, this pin here for ground, and then we need to wire in the MISO, but I need to check that the MISO outputs data and not receives data. I always get those two confused. So while we're at it, let's pull up the SPI bus. Although I suppose we don't really care, I can just resolder it. Yeah, I don't think we'll bother caring about that. SPI master, phase and polarity we'll probably be ignoring. Just going to check. We will have to worry about least significant bit and most significant bit first, but we can worry about that when we hit it. Baud rate. And we're not going to use CRC. Okay, so I can work this out. It's master out, slave in, which is a really good way of doing it because it means you don't have to worry about whether it's named from the perspective of being on the board and going out or off the board and going in. So we want master out, slave in, not from that, but from this. Master out, slave in is that pin there. So I almost ended up selecting the wrong pin. Let's snip the cable and get onto micropythoning. Actually, how are we doing for time? 15 minutes. That intro is really, really annoying. So from the time I click start streaming to stuff being visible at YouTube's ends, about 15 to 30 seconds. And that delay is actually a bit difficult to work with, in all honesty. And that's with the low latency enabled, which is just crazy. I said the other day I don't think Google understands what low latency means, and I think this just proves it. Cool. Not going to need that tool, so I'll put that aside. Now, you've seen me tin the ends before I soldered them in the past. Because there's a bunch of tiny holes where the golden pads are, that would actually be a mistake. I wouldn't be able to get the wire through the holes if I solder them. So let me just remove the oxide layer. Because these boards are actually, I got them when they first came out, and they've been around I live near salt water, so I'm very used to things corroding. So cleanliness is definitely a benefit here. Let's chuck that out of the way. And then look at the board. That goes up. USB goes up. So that's 5 volt USB there. And then that's ground. So there's a couple of pins that are larger than the others. So having a look at the board, the top one is ground. That one's 5 volt. So I'm going to have to give myself a bit more space on the cable. And what I'm going to do is solder the furthest one away and let that dictate everything else. RxTX. So this is from Y positions, X positions. Oh, that's interesting. Okay, it is the bottommost pin anyway. So it should be good. Yeah, it's that one. It would be nice if they had given a diagram from the bottom as well. Oops, I probably didn't strip enough wire off the end there. So I'm going to need the wire strip a bit more. I definitely want to try and make this as easy on myself as possible, so I can make sure it sticks a significant amount through, and I'm going to twist the wire, and I'm also going to remember what direction I twisted it in, and because I'm using my right hand, for me that's normally clockwise. Because when you twist it into the board, you also have to twist it in the same direction or you'll risk it coming undone. And let's fold that over. Good. Okay. So let's do a quick solder job. Once again, like this, because this powers up and turns off stupidly quick. So if I can get to the programming part in the next 10 minutes, that means we will be on track for a 1-hour video. I did kind of plan 2 hours, but I really ideally want it to be 1 hour because I don't know how quickly I'm going to actually honestly fall asleep. It's been a very, very long day, and I think I only got 2 hours worth of sleep last night. So, okay, that's above 300. Just tin the soldering iron. Feed that solder in. Cool, that's good enough. And then one thing we'll have to do is make sure that that doesn't fall off the table. Really not working with a lot of space here. The one thing to do is trim off the excess cables because, or wires I should say, because I bent them over and it's very, very easy for them to sway and short circuit on one of the other pins. Luckily the pin next to it is a data in pin, so it would be joining this pin here and that pin there, which is, oh, that's also a transmitter. It should be fine though. Shouldn't be too much of a problem, but it's better to not do it. There we go. Oh, people are actually commenting. I'm not used to this. Hello, Porter. I'm sure I did mean fun. I don't know how long ago that comment actually was, though. Okay. Must admit, I'm doing this pretty quickly, which is good. Like, live demos, it's really easy to make mistakes, so I think I'm doing particularly well. Okay, now I'm paying attention to chat if people are actually asking questions. So I've seen varying amounts of people ranging from 2 to 3, and I'm pretty sure I am one of those people. So congratulations if you're that other person. You know who you are. I mean, you can tell just how tired I am because my speech is really badly slurring. Okay, that goes through there. Actually, now I'm regretting not setting up the additional lighting, because this is actually pretty difficult to do. I really need a light behind me to be able to pull this off. Okay, maybe I will tin these wires. I just have to be extremely careful with how much solder I put on, because we will literally be threading the needle, so to speak. Oh man, talking of cowboys, wow, did I get that comment today? Well, actually, funny enough, I got that comment not from work, but from YouTube, with my previous build on Tuesday, was it? But, oh, it's still heating, that's why. Yeah, I don't know if you heard the story earlier, JP, about someone at work talking about adding in S3 and Nextcloud and something to do file serving and how they miss object store and everything like that. And I'm saying, well, do you realize that's like with a single dependency, you've added like 10 million lines of code to your project for something that's like a 30-line project. And they said, no, they're trying to convince us to like bypass a firewall and set up a VPC to serve up assets from S3 that are only ever going to be used internally. And I turned around and said, like, I've got this set up, like I set this up last week for a different project, like why don't we just use a web server? And they basically turned around and said, what's a web server? Yeah, well, watch the beginning of the video. I started off with that in this talk. Kind of blew my mind though, that someone fresh out of university was familiar with cloud technologies, but not how those cloud technologies worked, and was just not willing to accept the simple solution there. Okay, that's all been tinned, that's good. Yeah, I wish I was kidding. That's the third time in a week I've nearly handed my resignation in on the spot. and I wish I was kidding. But I'm seeing stuff, they're getting into web development and seeing stuff like that on an almost daily basis, and them coming to me and designing systems when it's our responsibility to design those systems is just really getting frustrating. Okay. And we're through. And I can hold that there. It's tiny, but I managed to get it in. And yes, I did leave that one open for jokes. Use your imagination. 1, 2, 1, 2, ground. VUSB. Yes, Scary Ghost Tales. Wow, that would probably be a better idea. Actually, I started the stream with, I worked in the web space and I've seen stuff, and I'm pretty sure you'll agree with that sentiment, considering you've got the same background as myself. Actually, to anyone who's watching my stream on YouTube after the fact, so I used to work in the web space doing DevOps type stuff before DevOps was really a thing, and all the chat ops and all that hype. And I'm now at the point where I've got enough skill that my solutions look stupidly simple and deceptively simple. But now I've gone into IT for finance, and they're about 10 to 15 years behind. And they're now trying to get up to speed, and it's kind of scary. Not going to lie. Some of the stuff you see, it's like, we've solved that problem 5 years ago. Why are you reinventing it from scratch? Are you that bored? Well, my favorite one is having explained that the limitation they've got is not really technical in nature, but actually physical, in the fact that physics is getting in the way of being any faster than they want to, and that they can't outrun the speed of light. And this is for a company that measures things in nanoseconds. I'm pretty bitter these days. I've seen the effects of hiring interns and only university students and no experience hires. And I suddenly understand startups. I'm going to offend so many people when they watch this stream. It's going to be great. Oh, this is an incredibly delicate solder job. Okay, I'm going to be quiet for a sec just because this is a very... I'm actually using the wrong soldering tip. Okay, so we just did a hot swap, and I swapped over to a... can I get to the camera? I went to a finer tip compared to a chisel tip here. So, like the pads I'm dealing with are about 1 millimeter wide, and my hands are getting a bit shaky for tonight. So doing that with a chisel tip, likely not a smart move. That's how you break boards like this. Okay. Cool, we up to temperature, we're up to 300, perfect. Oh yeah, I'm kind of talking and streaming because I'm so worn out after today. I spent all day yesterday in meetings having to make decisions that normally would take me 3 days in 3 seconds. It's like, design me a complete solution or I'm going to invent one myself. Okay, give me a sec. Well, I think if we do A, B, and C, we should be good. needless to say, it's been a breakneck pace for me all week. So that's good. We're going to cut that off. Okay, no solder bridges. You have to get the light at just the right angle to be able to see some of these small things. And I'm using two lights here, so one here, and you can see that halo, and another one right there. Normally I'd have one behind me as well, and that would get rid of some of these shadows you're seeing on the table. But the reason you want to be using bluish light, and I'm using 6500 Kelvin light settings, is the bluer the light, the easier it is to see imperfections in solder joints. So fluorescent lights are great for inspecting solder joints. The flaws just stick out wonderfully, and that's why it's so difficult to shoot some cars, because if you've got any scratches in the paintwork and you're using a bluish light under fluorescent lights, they suddenly become very, very visible. Okay, so micropython board has USB thing. I have USB here. Plug that in. It should light up. Hopefully you saw that flash. And bring that here. PyB flash. There we go. So this is the file system on the board itself. Main.py, I believe, gets executed. Mount media. So cat. Yeah, I'm not going to be able to type tonight. So we set the country to AU. Run the script after storage. So I could do this interactively. And that is a bit of a pain. So I could connect via the serial port and just type my commands in, and have it work. Or I could just write a script to do it. And I think I might write a script. But what we're going to do first is just test that I don't burn myself with a soldering iron. Let's put you away, because you're still probably about 200 degrees Celsius. Don't want to cut myself with that. We're going to write a quick and dirty script. So, oops. If you have a feeling about which text editor you should use, please be quiet. I don't think it's actually relevant. I like Nano, and I'm particularly good with Nano. Nano main. So let's do some quick programming. Bam. LEDs. From PYB import LED. LED 1. There should be I don't normally program on this machine, so all my settings are actually off. Timers. I need sleep though. Oh, you know what? It's the same as Python. Some stuff is different, others is not. I know from memory that 0.2 is a bit too fast, 0.5 is too slow. Okay, so... And actually I'll do that again because that's actually interesting. It's got a disk indicator light on it, so it lights up, which is cool. And we restart it and it's executing the code. And you can see the red LED flashing. So we know it works. Really, really nice and simple to program with. So that means that we only have to work out timing, work out the bit pattern to send out on the wire, and then start sending it out. So I think I have to hold that one down and reset it. There we go. Yellow I think means disk mode. And awesome. The reason I go out and back into the directory is because of cached file system stuff. Don't worry about it. It's Linuxy. Well, actually, if you do want to ask questions, go ahead and ask them. My main.py has disappeared. That's interesting. But it did run my code. Oh, you know why? I did the factory reset on that one. So you can see the country went to US, which is not a problem because it only affects the Wi-Fi channels that are available. So let's get rid of that battery first. We have to do a couple of things. We're going to take this path. No, we're not. We're not going to use screen. We're going to code, make directory LEDs. And I'm just going to quickly check something. Perfect, I've got make installed. What is it? Oh, you know why? No, it's not that. This is not looking particularly good, I'm sure. That's what I wanted. So there's a default key bindings, and then there's the key bindings I use on a day-to-day basis. I need that path again. Media. It's pi something. Pi b flash. So this is going to look very similar to my usual development process. Not identical. Cool. Good. And okay, so we want to copy anything.py to destination make. Perfect. Now, if we ls media touch main.py. Actually, let's cat media and make. Good, it's empty. Okay, so we have a simple deployment mechanism. It's just going to save me typing a bunch of stuff, and I don't want to work directly on the SD card because, as you saw, I just completely blew away my code by accident. So let's put you over the top of that, and we need a couple of things. So we need to bring in the SPI driver from pyb import SPI is equal to SPI1 SPI.master baud rate, which we will calculate later. Polarity equal to 1. Phase equal to 0. Cool, and we are going to be writing, so let's check out boot parameters are correct first. Mode, SPI master, yep. Baud rate, we calculate later. Prescaler, polarity, the idle clock line sits at. We don't care about that because we're not using the clock line. Sample the data, phases on read, we're not using that, so those can both be omitted. Phase and polarity, which simplifies things. Bits is equal to 8, which is good. We need to worry about first bit, which is if it's least significant bit first or most significant and we are going to go LSP, so least significant bit first, not for any reason other than it was the first one that came to mind. TI is false, and we don't have a CRC. That's good. Now to send data on the wire, we do SPI.send, and buff while true. Wow, I'm really not doing well today. Buff is equal to bytes 1, 2, 3, 4, 5, 8. That's fine. I don't have to be perfect. So we're going to send the bytes, and then we're going to rotate the bytes. So we take, I need another Python window. I can't remember what the API for bytes is off the top of my head. I need a pop. Can I shift? No. Okay. So let's do that. Buff is equal to buff the second character and everything onwards plus the first character of buff. And that's got to be a list, I think. Buff, I don't know actually, let's quickly check that. So let's invoke IPython again. I want to create a buffer object. Interesting. Let's give it a list. A is equal to that last value, a. Don't know why that converted that to a string. That's really, really kind of bizarre. Actually, I'm just going to use byte array. This is why people normally don't do live coding. Yep, okay, that's what I want. A is equal to that, A0, A1 to onwards plus A0. As I thought, so do I have to go like that? Oh no, we lost the stream. That's coming back. I saw a segmentation fault, so I might have accidentally clicked the close button, which I can do if I'm not paying attention. Anyway, basically we worked out the syntax. I set initial values of what I want the LED colors to be, and then what I do is I just rotate them through the strip. So we should end up with the colors. If that was white, it would start going all the way down and then repeat. So let's work on the code a bit more. From time import sleep, and then we sleep for 0.2 seconds. Okay. 0.2 seconds. That's looking good. We have to do some more work on this. So this is going to be where we have a bit of trouble with the SPI clock frequency stuff. And this one. So I need to work out if we're using SPI 1 or 2. So we're using this SPI, and that's on the X position. So SPI 1, and I think from memory, yeah, we specify 1 to the SPI object, so that's good. So I suppose we should go into the protocol of the LEDs a bit, because that's actually a bit important here. Basically, the width of the initial pulse determines if it's a 1 or a 0. So for simplicity's sake, we want to divide this into 4 time zones, so that we can store 1 bit, so we can store 2 bits in a single byte. We could probably get away with 3 bits in the final output buffer representing one of either a 1 or a 0, but then that doesn't evenly divide a byte, and we have to do a whole lot of bit shuffling, which becomes difficult. So it's easier just to deal with top byte, lower byte, and if you're using powers of 2, the math becomes simple all the way through, and you can optimize quite a bit. So first things first, we're now what? Well, it's saying 2 minutes, but the stream's been going on for longer than that. So I'm going to have a quick drink, because my throat is starting to kill me. And to be honest, I could do with the caffeine. So the other thing we'll be able to work out is whether or not we need to send the least or most significant bit first. Oh, that's better. And we're dealing with 24 bits at a time, so that'd be RGB, both at 8-bit values. Okay, so composition of a 24-bit data. Following the GRB, send data in the high bit sent at first. So we want to send most significant bit first. That's easy enough to fix. Okay, now we have to worry about a couple of things. One, the buffer size. We have 8 LEDs. So the length of buffer is going to be 8 LEDs times 3 bytes per LED. Oh god, if I can type. 3. Now that should be 24 bytes. And then we have to halve that, or do we have to double that? I think we have to double that for the bit bang IO. Okay. Let's work out the timing first, because that's going to be annoying. So we've got some timings here, T0H and T0L, which is T0 high and T0 low, and T1 high and T1 low. And here we go. So in total that adds up to 0.25 of a microsecond. And we've got the ability to move that up and down by 600 nanoseconds. So we could overclock this quite a bit. But what I think we'll do is, rather than use 1.25 microseconds, we'll use 1 microsecond, because we're still within this tolerance of 600 nanoseconds. So that means if we divide that by 4, because we're going to have 4 bits represent a single, so 4 bit bang bits represent and 1 output bit. We can then just divide the timing by 4. Okay, cool. So that would mean 0.25 microseconds here, which is actually out of bounds. So we want to stay within that. So how much are we out of bounds by? So we subtract 100 microseconds from 0.4 to become 0.3. So as long as we're above 0.25 microseconds, we're actually within tolerance. And note that this number and this number are the same, so that does make things a bit simpler. And if we take one, oh no, okay, so we're actually, that's within tolerance. If we take 1 second and do that, that's good. Let me draw this on paper because it should hopefully make a bit more sense. So if we've got T total, okay, which is 1.25 microseconds plus minus 600 nanoseconds. So there's that. What we do is divide that into 4 like that. And then we divide that up. Actually, let me draw the 0 and 1, and we can do that. So each of these gaps here, there, and there, like that, they're going to be 0.25 seconds in width. And if you go off and run the numbers on the tolerances, and I know because I've actually done BitBang this way before, and the tolerances are actually significantly, you can get away with a lot more than they actually state there. So we're just trying to make it easy on ourselves, basically. So 250 microseconds. So we have to set the SPI bit rate to emit a bit every 250 microseconds. And if we do that and we put through specific bit patterns, in the case of 0, I did misdivide that one, 0, 0, 1, 1, 1, 0. So if we have a look at this, if we want to send out a 0, we send the bit pattern 1, 0, 0, 0. So one bit fits into half a byte or into a nibble, so we can send 2 bits per byte. And then the 1 we send 1, 1, 1, and then a 0. And all our timing matches, and I think we can send it to the SPI device like 16 bytes at a time and just have it transferred in the background. So most of the time we should be idle and doing nothing, which is really, 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 really nice. It should be ultra low power. That is apart from the LEDs, which are 18 milliamps per pop. Okay. What do we want to do next? We need to work out the SPI bus timing. Not fun. I think I might even need a manual for this, and that's the worst part. Okay, so ITC is very, very similar. That's nice to know, because that's all sitting here. Frequency, IDD, SDA, we don't care about that. Integer, which sets the maximum frequency for SCL, 400. So I'm hoping I can just put the baud rate I want into here and have all the math done for me automatically. So what bit rate do we want? We are sending a signal every 250 milliseconds. I should know this off the top of my head. What we're going to do is use a calculator. Once again, we're going to use Python as a calculator. So I've got 1 second, and I want to divide it by 250 microseconds. So that's millis. Do I have my math right? Yeah, 250. There we go. That can't be right. .2, yeah, no, we should be dealing with nanoseconds. Sorry, I've got that completely wrong. Okay, so we want a 4 megabit data rate. Now, 4 megabit is not a lot for SPI, in all honesty. It's pretty good. So I'm actually going to make it simpler on us and have the code do all the calculations at runtime. So we want bit rate is equal to 0 dot bit interval over God, 1, 2, 3, 1, 2, 3, 3. We'll actually confirm this in a minute. I want to do it this way because if I do have an issue with my timing, then this will make it very simple to work this all out. So let's make sure I get, God, I'm going to have to reselect that. This is not my default programming environment. That's always annoying. So bit interval is, good catch. I actually can't remember how to do this. Oh, yep. There we go. So 4 meg, yeah. Now I have to be careful because I don't think this board has floating point, but I think we can do slow but basic floating point on this. And let's just check the messages. Cool, so I shouldn't get distracted. So we now want to set the SPI bus. I've now got an ordering issue. Bit rate. And what we want to do is do a 0 is equal to and a 1 is equal to, how do I represent this? That is a good question. 0b 1 1 1 0 0b 1 0 0 0. Okay, we're going to have to fiddle around with that. We've actually got a couple of different bit endiannesses. We've got one both from the point of view of the SPI bus, and we've got another one from the point of view of the bit packing, and we have to make sure that everything lines up. Luckily, if we get it wrong, the colors are going to be completely whack. So I'm actually not going to try and work it out. We're just going to brute force it later. So we've got the SPI rate up, we've got that up. We now need to work out what's sent on the wire. And this is going to be interesting. Oh, this is actually going to be really, really interesting. I have to do data on top of data. So I need an auxiliary function to generate the waveform that we spit out via the SPI bus, and then we need another one to take 3 colors and spit out something that can be consumed by the waveform. So let's do def RGB to, I'm just going to do RGB to bits. RGB. The other reason I'm doing it this way is I'm normally familiar with RGB, and I think this is actually packed as BGR. If I had that right. Green, yeah, GRB. So we'll do the conversion later. And we're going to return something. For the moment, I think that something is going to be 3 bytes wide. Yes, it's going to be 3 bytes wide. And GRB. Just going to do that for the moment. Maybe this function is not required. Live coding is stressful and annoying. So colors to bits. So colors to bits should take 3 colors and return bytes that can be sent out. So that is essentially what this is doing. So I've got this as duplicated, but I like this name better. So we're going to go with RGB again. Kill off this. So this will return 3 bytes because I need to return 24 bits. And then we've got to take those 3 bytes and then expand them to the bit waveform, and then return the bit waveform and then send that out to the SPI bus. Yes. And I'm also forgetting something, which is a reset is equal to 0b00, I think it's 4 bits. Ret is T reset. T reset is anything above 500 microseconds. Now, 50 microseconds. Oh, that's going, so 250 nanoseconds. 50 50 divided by 0.25, 200. Okay, that's a lot. So what we can do is cheat OXFF, no, 0, 0, and I need, oh God, 250, but it's going to do a byte at a time, which is 5, so I only need 100 of these. Why? I should be able to math better than this today. And I'm going to have to do some type conversion. So byte 0x0. It's going to be a byte array, doesn't it? Times 100. That actually might take a second parameter now that I think about it. Array. No. Well, that's easy enough to fix. Byte array is equal to that for I in range 100. Okay, so this will generate a full, so this reset is a full waveform that I can just send to the SPI send to reset everything. And in fact, we'll do that. SPI.send receive reset. Not my best day today. Okay, colors to bit. So we're going to pack each of these independently. If we start from the least significant, so we're most significant bit first, but we want to actually unpack from the least significant bit. So let's do this backwards, and then I'll be able to reverse that later. Range 8, because a bit byte is 8 bits. Oh, okay. Bit is equal to color. Wow, why? And 0x1. So that'll give us a result of the lowest bit and should always return either 0 or 1. Bit manipulation is definitely not Python's strong suite, but there, at least under MicroPython, it's a bit easier because you can guarantee some of the types. For color in GRB, that's how we're going to swing everything around. Okay. And what we're going to do is have a buffer is equal to be that and return buffer. Okay, cool. Now I want to check something if we've got that, and I'll put that on the screen to make it a bit easier. A plus to a dot extend, append, add, no, okay. So I do need a byte array, and I need to check out what the byte array has. Append, it does, okay. So we'll go off and fix that here. And from memory, byte array, yep, just returns that. Is equal to that, a dot add, append, and I can append integers. Ah, perfect. Okay, and then if I do that again, that's looking great. So while I can't just do a dot append 1 or 0, because I have to take these two sets of 4 bits and pack them together. Once I've got that fine, if I deal with bits 2 at a time, this is going to be a lot simpler. So maybe I actually want to do this via... Let's actually process these 2 at a time. So the two lowest least significant bits are 0 and 2, and added together that's 3. And then we can append to the buffer so we've got a couple of cases here. We've got 0, 1. Maybe I should have just done this off stream, to be honest. This is not going to be beautifully edited. So in this case, we would end up with something like 0, 4, or 0. And that will return a byte. Yeah, I'm not in my favorite chosen environment at the moment, which is all my key bind. I'm making silly mistakes with my key bindings. Copy, and I'll just go Control V, Control V, Control V. And I'm going to just check one thing, bits. Bin, perfect bin, and I want 1 shifted 4 positions. Yep, okay, that does exactly what I want it to. And we can change the packing very, very easily by modifying this table. So we're going to do a quick lookup, which will be bits. And then for each one of those, we just do buffer.append. I'm going to call it A for the moment. It's crappy code, but this is basically proof of concept more than anything else. And then once we've done R, G, and B, we end up with a full waveform for one single color to bits. But we should be able to, yep, A plus A, yep, we can just add them together. So for every LED, we can chuck them into a list and then either process them LED by LED, or we can just generate the full waveform and then just send that all in one go. The data is quite mutable in that regard. So let's work out the bit pattern. And let's actually make this easy to understand. One 0 and 1 1. Nice and simple. OB 0 0. Yep, that's good. Cool. So this one's obvious as to what it should be. 1 1. So I'm actually just matching it off the bit pattern in this column here, which is kind of nice. Oh, hello, where did... I just realized that Windows... Why did you swap around? You should be on there. Mistakes were made. A lot of mistakes were made. Kind of wish someone had flagged that before. So back to where I was. I matched the 0, 1 and 0, 0 to what I've got here. Nice and simple. And I'm going to line that up because I have a good feeling I'm going to have to fix it up later. Okay. We're also going to do some presets here. Now I'm using RGB. Oh, actually, you know what? I can actually even pre-generate these, so that's nice. Colors to bits. Zero, 0, 255 is, it's an 8-bit integer. And 25500. Actually, this is one of those, I'm not normally a fan of being able to type very, very quickly, but this would probably be one of those occasions where I'd want to be able to do so. So let's go red, red, green, green, green. I really can't type today. Blue, green. I've had a lot of issues programming at work, and I'm actually starting to wonder if it's just the desk and the setup that I've got here that's just not comfortable for me doing that. Okay. We're going to regenerate this on every iteration, I think. Yep. Byte array. We'll just do that. Then for LED in LEDs, buff dot append LED. Okay, that's looking good. Then we send it down the wire. We then do a reset. And I don't know if we have to terminate with a reset sequence. Yes, we do. Okay, so we do have to do the reset. And then we do a rotation. And then we go to sleep. So we're actually going to modify buff to LEDs and all. There we go. Ow, I actually just shocked myself off the Pi board. Must have been a ground loop. Okay, so I think we're getting there. This is going to return some stuff. Python 3 module compile all main. Perfect. And what we're going to do is take that and you'll see what I'm doing in a sec. Cool. Test. So we're actually just building a very, very simple sanity check, because otherwise I will do typos all over the place and not notice it till it's too late. Okay, so that was set up automatically. Cool. Line 6. Oh, why'd that happen? Okay. Done. Okay, we're on the board. How are we going to do this? We are going to reset, I think. And the Pi board came back. I actually don't know if my code... Well, you know what I should be doing in my code, actually? Is setting up a flashing routine. So we actually had that before, so let's bring that code back up. It was a quick reference for the LED, internal LEDs. B import LED, that was LED 1, LED is equal to LED 1, and then we just do LED dot toggle. Perfect. And then we do a, well, actually I should download the code there first. And that is 898 bytes and not 0 bytes, that's good. So we do a reset. The LED is not flashing. Try the other button. Okay. Which means, I think from memory, there was another boot file I had to take care of. So copy boot. So let's fix up a couple of things. One, main file is that. Make sure we're using the local stuff for that. Cool. Then we do a reset. That came back. Let's take a look in this. So I can see my changes. Run on boot up pyb.main. We're not seeing the LED flash, so I just want to quickly ensure that code made it there. LED 1, LED dot, that'd be why. I'd like to say that I'm normally focused and don't make stupid mistakes like this. I tend to get the complex stuff right, and the simple stuff like this is where I spend most of my time debugging. Okay, that's good. And once again, we'll just check this. Text editor, led.toggle. So our code's not executing. I'm expecting to see that LED there flash. There could be a number of reasons for that. And I want to check one thing. Groups, grep, dial out. Do I still have that? No, I don't. Change owner, Blitz, dev, tty. So we're going to do something interesting. And I don't have code installed, do I know? We're going to do some live debugging. So we can actually connect via the serial port that it spits out. Oh, that's interesting. And once we do that, we can do things interactively. I suspect there is a code error, whether it's a missing module or something like that. Cool. Now I'm going to show you a very, very little known feature of Screen, and that's it can actually talk to serial ports, which is one of the reasons why I use it over Minicom. There we go. Let's have a look at our main.py. So open with the text editor, copy that. And we're not going to test it line by line, but I just want to check the imports work. Okay, cool. I mean, it could be simple that the code is actually running, but that I just chose the wrong LED. So it's flashing when I manually do it. So I did have the right LED. Okay, that's not a good sign, but I do want to see if LED 2 is available. Oh yeah, it's an RGB LED. What do you know? It's kind of nice. So let's have a look at boot.py as well while we are at it. And interestingly, that's not doing anything. So I probably do not understand enough about, or more likely I've forgotten, about how the boot up sequence on this board happens. General board information, start, stop. Boot.py and main.py files to search for. Boot modes, here we go. File system reset, which is what I did earlier. So I accidentally reset the file system by holding that button. Holding this as it's booting up, hold down the user switch, and press reset. The LEDs will count in binary. Okay, so we want green LED mode. So hold down this one. And you can see my screen session terminated. Still not seeing the LED blink. I wanted to see if it just came up as a flash drive, and it did come up as a flash drive. So the plot thickens. It's really hoping to be further ahead than this. I'm probably going to I'll give this another 10 minutes and see if we make progress. And if not, I'll cut this video up so that there is magic tomorrow when I do actually have this working. File system becomes corrupt. ls-that, change owner. Now, it may seem like funny that I've got sudo access without a password. That's actually enabled for a very, very specific reason, and that's because you can see my keyboard, and if I type my password while I'm on stream, bad things will happen. Pieboard, flash. Okay, so I didn't actually see. Let's try that again. It's talking about error flashing LEDs if there is a problem with the a REPL and how to connect. Okay, so let's reset it. Starts up. It's looking good. I'm not seeing any issues there. So let's move the LED initialization code earlier. And in fact, red and the other one's green. So we're going to make the startup LED red.on. And then once we've gone through here, LED red.off, and then we will toggle the green LED. Okay, that's downloaded. We now try again. Okay, so that's really, really interesting. Green standard boot, safe boot. And then flashing. So we're not getting flashing, so there's not any errors. So I can only think that there's a problem with the logic in my code. But we're not even getting to these first two statements, right? So the issue's got to be in like boot.py. au main.py, run arbitrary code. Hell, let's just steal the code from here, I guess. Actually, let's be a bit smarter than that. No, okay. Really not liking my chances here. Really hating this keyboard with the FN and the control being swapped around as well. Thank you, Lenovo. Okay, it's looking good. Let's try our code once more and see if I'm sane or not. And nothing. Okay, I'm going to make sure I'm just resetting this properly. So override this when you power up normally or press the reset button. Boot.py will be configured and then main.py will be run. Okay, so if I just go like that. and still nothing. That is very, very interesting. I can see two possible causes here. One could be line endings of all things. Oops. But what I think I'm going to do is call it here and do a follow-up streaming where I do actually have this working. The hardware's here, the prototype at least, so I can try out getting the LEDs lighting up. Once I do, I can build a whole lot of accessories such as street lights, stadium lights, lights for the cars themselves, and then configure them all over Wi-Fi and hook them all up together and even control them from a central location. So that's the end goal. This is going to be for the rally truck, but I'm looking long term to make this available as a product. It would be nice if you could buy a whole lot of little street lights that you could put around your track and they light up and they can detect when cars are coming and, I don't know, flash colors or something, and basically be able to light up your tracks without having to use downlights like I've got. They should be relatively cheap because I found some rather cheap boards for this, so we'll see how it goes. Thanks for joining me. Thanks to the people who actually chatted. Please leave some comments if you want me to clarify things when you view this on YouTube, and I'm more than happy to answer questions. There will be a follow-up, and that follow-up will probably be this video plus some additional footage from the weekend where I do have this completed, and it will likely be shorter than the raw stream. So keep on building, and I shall see you all around.